This is lesson 22 in our Calculus 3 series, Double Integrals over General Regions. In lesson 21, we define the double integral of f over rectangle R by partitioning the x and y intervals, which gives us a partition of the rectangular region R, and then taking Riemann sums and taking the limit as the maximum delta xi and delta yj go to 0. And we recognize that this double integral gives us the volume of the surface under the graph of f of xy if f of xy is greater than or equal to 0 on R. Otherwise, we have to keep in mind that the volumes that are under the xy plane will get a negative sign. And we compute the double integral using Fubini's theorem. So we compute the double integral by writing it as an iterated integral over that rectangle. Now we're interested in volumes over a general region in R2. So let's say our domain D is here, and this is what we are integrating over. We want to find, for example, the volume under this surface over the region D. So what we need to do is define a double integral over a general region, and then also talk about how to compute an integral like that. We're going to start by partitioning a rectangular region that covers our domain, but we're only interested in computing our Riemann sums over the subrectangles that are entirely within the domain. So for example, in this picture, we want to compute only over these identified subrectangles. So again, we partition a rectangular region that is bigger than the domain, but we're only going to compute over those subrectangles that lie entirely inside the domain. We'll number these rectangles R1 through Rn. In this case, we have through R11. And that's going to define our partition P over the subset of the domain over which we're integrating. And then we're going to talk about the norm of P being the largest length or width of any of those subrectangles. And we're introducing this notation just to have a nice, concise way of describing the limit here. The evaluation point we'll call xi star, yi star, that lies in Ri, and delta ai is the delta xi, delta yi on rectangle Ri. So our double integral is going to be limit as the norm of the partition goes to 0. In other words, as the length and width of those subrectangles goes to 0. And we're taking the sum over all of those rectangles of an evaluated point. So we've got a height here times the rectangle's area. And to compute these integrals, we need to recognize the domain as one of two types. A type 1 domain I like to call a top-to-bottom region because it can be described by a top function y equals g2 of x and a bottom function y equals g1 of x for x values between a and b. So x goes from a to b, y is going from g1 of x to g2 of x. A type 2 domain I like to call a right-to-left region, and here we can identify a right function, x equals h2 of y, and a left function, x equals h1 of y. And here, y is going from c to d. So our domain looks like this. X is between h1 of y and h2 of y, and y is between c and d. Now you might be wondering, well, what if our region can't be described as a type 1 or a type 2? Well, in that case, then we just have to break it up into smaller regions that can be described that way. So this complicated domain here can be broken up into these 5 regions. This one's a type 2, it's a right to left. Here's a right to left. This one's a top to bottom. This one's a top to bottom. And this one's a right to left. I'm sure that's not the only way to break up the original domain, but it is one way that we can break up the domain into type 1 and 2 regions so that we can set up each of those integrals. Now for our type 1 integrals, remember here we're saying y is varying from g1 of x to g2 of x, so we're going to first integrate on y, then integrate on x, and x is going from a to b. For integrals over a type 2 region, we're describing x as varying from h1 of y to h2 of y, so we're going to integrate first on x, then integrate on y going from c to d. Keep in mind that with either of these integrals, the bounds that are curves, functions that have variables in them, have to be inside bounds. Okay, the bounds that are functions or curves have to be inside bounds. The outer bounds can only be constant. So for example, find the double integral of f of xy equals 24xy squared over the region bounded by y equals x squared, y equals 16, x equals 1, x equals 3. First thing we want to do is identify this region in R2. So let's sketch that. We've got y equals x squared, that's our parabola here, y equals 16, and then x equals 1 and x equals 3. These are the bounding curves for our region, so it must be this shaded region here. Now we look at this and do we want to slice it top to bottom or right to left? You could do it either, but with top to bottom, you have one curve on top, y equals 16, and one curve on the bottom, y equals x squared. That's going to be a simpler setup than a right to left, because if you go right to left, you've got to split it here, because our right curve for this top part of the region is x equals 3, but our right curve for the bottom part of the region would be x equals radical y. And to avoid splitting up the integral, I'm going to acknowledge this region as a top to bottom region and go with a type 1 integral. So I'm going to describe my region as x going from 1 to 3, y going from x squared to 16, right? This is y equals x squared, this is y equals 16. And notice that y is the variable that has another variable in its bounds, so y has to be the inside variable here. Y varies from x squared to 16, and then x varies from 1 to 3. So we integrate on y first, and then on x. So integrating on y, this 24xy squared becomes 24xy to the third over 3. And our bounds are 16 and x squared. So remember that we just integrated on y, and so the 16 and the x squared are getting plugged in for y here. So I plug in the 16, plug in the x squared, and simplify. So now we're here and we want to integrate on x. So we integrate on x, plug in our bounds, and subtract. The numbers are a little bit large here because of the 16. Let's take a look at another example. Find the double integral of f of xy equals 2xy squared plus 2y cosine x over the region bounded by y equals radical x equals 0, and y equals 3. So the first thing I'm going to do is sketch my domain here. Y equals radical x equals 0, and y equals 3. So this shaded region is the domain over which we're integrating. And we recognize that this could be a right to left or a top to bottom. So we could set it up either way or both ways and see if maybe one of the integrals is easier than the other. So we'll set it up both ways. As a type 1 top to bottom, we've got y equals radical x and y equals 3 as the bounds on y, so we have y between radical x and 3. And then we have x going from 0 to 9. So that integral is going to look like this. Again, we're integrating on y first because y has an x in its bounds. Or we could identify this region as right to left, and in that case this is going to be y squared is equal to x, so x is equal to y squared, and this is x is equal to 0. So we've got x going from 0 to y squared, and y then going from 0 to 3, from 0 to 3. So because the x has a y in its bound, that's going to be the inside variable here. So we're integrating dx then dy, and the bounds on x are 0 and y squared, the bounds on y are 0 and 3. Now either one of these integrals is reasonable, but personally I like squares better than radicals. So I'm going to choose this one and we'll go through that. And I encourage you to go through this integration as well. You'll notice that it is a little bit more involved because you'll need to use an integration by parts here that you don't end up needing with this integral. but it's certainly a reasonable integral to solve. So I encourage you to solve that as an exercise. Let's take a look at this one here. So we're first integrating with respect to x. So we have x squared y squared. And then the 2y is a constant multiple, and we're integrating cosine x, which gives us sine x. So we're here, and our bounds are 0 and y squared. We just integrated on x. We're plugging in x equals y squared, x equals 0. So x equals y squared, here and here. X equals 0, here and here. So that gives us y to the 6th plus 2y sine of y squared. So integrating with respect to y, we get y to the 7th over 7 minus cosine of y squared. Because notice here, what we have is a u sub. U is equal to y squared, and du is 2y dy. So it's actually a perfect u sub. We don't have to make any adjustments here. This is integral of sine u du. That's negative cosine u plus c, or negative cosine of y squared here. And plugging in the bounds, 3 and 0, and subtracting, don't forget cosine of 0 is 1, so we have 2187 over 7 minus cosine 9, then plus 1, so we've got 2194 over 7 minus cosine 9. And as I mentioned, you'll get the same answer using the first integral, but you'll be using an integration by parts with this one. Let's take a look at another example. Find the volume of the region in R3 bounded by y equals x squared minus x, y equals x plus 8, y equals 2, and then z equals 1, z equals 5 plus x. So they're giving us all of the bounding surfaces for this solid, and we want to find its volume. The first thing I want to do is get an idea of what's happening just in the xy plane. So I'm going to take a look at the first few equations that we have. Y equals x squared minus x, y equals x plus 8, y equals 2. With y equals x squared minus x, I want to have an idea of how to sketch this. So I want to complete the square and recognize that this is x minus a half quantity squared. But that would include a plus 1/4, so I need a minus 1/4 here. Right, so completing the square gets us here, and this helps identify the vertex of the parabola and helps us plot. We could see the vertex here is 1/2, comma, negative 1/4. Right, we're taking our parabola, we're moving it to the right by 1/2 and then down by 1/4. So that gives us the parabola here. We also have the line y equals x plus 8. Well, where do those two curves intersect? We can find that by setting x squared minus x equal to x plus 8. We find that x is equal to 4 or x is equal to negative 2. So we've got the parabola intersecting the line here. And we also have a line y equals 2. So I'm just going to make this part of the parabola dotted because it is not part of our bounds. So this is what's happening in the xy plane, and this is the domain over which our two surfaces lie. We have z equals 1 and z equals 5 plus x. So we've got two surfaces that are lying over this, and these make the top and bottom bounds for our solid. So let's bring this into the grapher and take a look at what's going on. This is our parabola, y equals x squared minus x. You can see in three-dimensional space it's a parabolic cylinder. Now we also have y equals 2 and y equals x plus 8. So this is the same region we just sketched. But now we're talking about a solid that has a bottom surface and a top surface. The bottom surface is z equals 1. It's the bottom surface there. And the top surface is z equals 5 plus x. Now it's nearly impossible to see the solid that we're talking about here, but it's inside here, right? It's underneath this plane, inside this parabolic cylinder, behind this plane. Now, while we're not able to really see what the solid looks like alone here, I think it does help to give us an idea of what we're integrating. So I'm going to call this domain D. And notice that we have a top surface and a bottom surface that we're trying to get the volume between. We've seen something like this back in the beginning of Calc 2 when we talked about the area between curves. We had to take two integrals and subtract. Same thing's happening here. We need the double integral over D of 5 plus x minus the double integral over D of 1. This is our top surface. This is our bottom surface. If we integrate 5 plus x over domain D, we are going to get the volume from 5 plus x down to the xy plane. And if we integrate 1, z equals 1, over domain D, we're going to get the volume from z equals 1 to the xy plane. So in order to get the volume between these two surfaces, we need to subtract these integrals. And by properties of double integrals, we know that this is going to be double integral over D of 5 plus x minus 1, or 4 plus x. So now the question is, how are we going to describe this integral? Is it a type 1? Is it a type 2? Do we need to break it up? Let's take a look at what we have. If we consider it a type 1 integral, top to bottom, then we're going to have to break it into 3 parts, because the bottom curve changes from here to here, and it changes again from here to here. So as a top to bottom, we would need 3 separate integrals. Let's take a look at describing it as right to left. Could we describe it as right to left? We could, but we would need 2 integrals in this case, because our left curve changes after y equals 6. So the question here is, do we want to describe our region as right and left curves, in which case we're going to have to talk about our functions here on the right and left being x equals positive, negative, radical y plus 1/4 plus a half, right? Because that's how we solve for x here. Or do we want to use 3 regions and have y equals x squared minus x as a bottom curve? I think it sounds much easier to use the 3 regions and have simpler functions to deal with. So I'm going to choose to do it that way. So I'm going to call this D1, D2, D3. And so our integral here is going to be equal to the double integral over D1 of 4 plus x plus the double integral over D2 of 4 plus x plus the double integral over D3 of 4 plus x. Now let's take a look at how to describe each of these regions. This top equation here is y equals x plus 8. This is y equals x squared minus x, both sides here. So D1 is xy such that we've got y going from, on the bottom, it's x squared minus x, and on the top, it's x plus 8. And x goes from, it looks like -2 to -1, but let's check this here. This needs to be the point of intersection between the parabola y equals x squared minus x and y equals 2. So x squared minus x minus 2 is equal to 0. So this would be x minus 2, x plus 1. And so that's x equals 2, x equals -1. So yes, this point is x equals -1. This point is x equals 2. So here we have x going from -2 to -1. And that describes D1. Y goes between x squared minus x and x plus 8. And x goes from -2 to -1. D2 has xy such that the top curve is y equals x plus 8, so y goes up to x plus 8, starts down at 2. Y goes from 2 to x plus 8. And x goes from -1 to 2. And D3 is xy such that, again, we've got the same top and bottom bounds as D1, but just a different x interval. This is 4 here. So we've got x squared minus x less or equal to y less or equal to x plus 8. And we've got x going from 2 to 4. So let's set up our integrals here. Integral over D1, we've got -2 to -1, x squared minus x to x plus 8, 4 plus x, dy dx, plus, we've got x going from -1 to 2, y going from 2 to x plus 8, 4 plus x. And for D3, x going from 2 to 4, y going from x squared minus x to x plus 8, again 4 plus x, dy dx. And we would compute these integrals. In the interest of time, I'm going to move on to another example. Here we want to set up two double integrals, one which is in the direction dy dx and the other dx dy, to find the volume of the solid in the first octant bounded by x plus y plus z equals 12. So the volume of the solid in the first octant bounded by x plus y plus z equals 12. Now we should recognize when we see this equation that this is a plane. And if they're saying that a plane bounds a region in the first octant, it must be that this plane intersects all of the axes, and we've got a solid region like this. So we need to figure out where this plane intersects the axes. So when x is 0 and y is 0, that's when we intersect the z-axis. If x and y are 0, then z must equal 12. Similarly, if x and z are 0, y must equal 12. When x is 0 and z is 0, y is equal to 12, so we're intersecting here. And when y and z are 0, x is equal to 12. We're intersecting here. So again, to find out where we're intersecting the axes, we set two of the variables equal to 0 and solve for the third. So now we can see that this is the surface under which we are finding the volume. And so we have to first describe our domain in the two-dimensional plane. And so what's happening in the xy plane here? We've got the line y equals 12 minus x. We've got x equals 0 and y equals 0. So we can slice this as a top to bottom or as a right to left, right? As a type 1 or a type 2. So here's our region as it appears in the two-dimensional plane with the x-axis here and the y-axis here. So if we describe this as a type 1 with a top and bottom curve, we're going to have y equals 0 on the bottom, y equals 12 minus x on the top. If we describe it as a type 2 right to left region, we're going to have x equals 12 minus y on the right and x equals 0 on the left. And in that case, y goes from 0 to 12. With the type 1, we had x going from 0 to 12. So with the type 1 integral, we have y varying from 0 to 12 minus x, so we integrate dy first. The bounds are 0 to 12 minus x. And then x varies from 0 to 12. With the type 2, we have x varying from 0 to 12 minus y. So we've got a dx on the inside, 0 to 12 minus y, and then y goes from 0 to 12. The dy with 0 to 12. Now notice what I have on the inside here, 12 minus x minus y. Where did that come from? Well, the equation for this plane, which is our surface under which we're finding the volume, is x plus y plus z equals 12. So we need to solve this for z and put that function in our integral. And so we're here. These are the two integrals that would give us that volume. Now we're going to talk about changing the order of integration. But before we do that, let's just actually compare these two integrals that we have here. We know these integrals represent the same volume. One's a dy dx, the other's a dx dy. Notice here that we can't simply just switch our bounds. 12 and 12 minus y, that's not what we have here when we switch the order of integration. When you're changing the order of integration, you want to start with your given integral. You want to sketch the domain from this integral, look at this, and then sketch the domain. And then from the sketch, create a new integral. So let's take a look at this example. We can't integrate e to the y squared dy. So we're interested in switching the order of integration. So let's see how that would look. What's the domain over which we're integrating? This says y goes from 3x to 3. Y goes from 3x to 3. So those bounding curves are y equals 3x and y equals 3. So let's sketch those. Y equals 3x, y equals 3. And with that, x is going from 0 to 1. So it looks like we're going to have this region in here, but let's just check by picking a point in here and saying, okay, what does the y vary from? Y varies from 3x to 3. And with that, what does x vary from? 0 to 1. Yes, we're inside the right region. Now notice this region was given to us as a top to bottom integral, as a type 1. If we're going to be switching the order of integration, we need to describe it in the other way. So if it was given as top to bottom, we need to now describe it as right to left. So this y equals 3x can also be written as x equals 1/3 y, and that's going to be our right curve. And our left curve is going to be x equals 0. So x is going from 0 to 1/3 y. And then with that, y is going from 0 to 3. So we forget about the original integral that we're given, and we create a new integral based on this. Of course, it has the same function that we're integrating, but the bounds are based on our new description. So we have x going from 0 to 1/3 y, and then we have y going from 0 to 3. And this is reasonable to integrate because integrating dx just multiplies this constant by an x. We plug in our bounds there. And now we integrate with respect to y. And now notice we have a u substitution here. U is equal to y squared. Du is 2y dy. So I'm going to multiply by a 2 and a 1/2. I'm also going to pull my 1/3 out of my way. This becomes then e to the u du inside our integral. We have a 1/6 on the outside. And notice that these are now bounds on u. Here we had bounds on y. When y is equal to 0, u is also equal to 0. When y is equal to 3, u is equal to 9. So we integrate here, plug in our bounds, and subtract. So again, the process with changing the order of integration is to start with your given integral, sketch the domain, and then from that sketch, get a new integral. So we started with this integral. From the given integral, we sketched the domain. We realized we were given it as a top to bottom, which means that we need to write it as right to left so we can switch the order. And so then we create our new integral. Let's take a look at another example. This is not something we can integrate unless perhaps by some formula in the back of your textbook. So we're interested in changing the order of integration. So we look at the way our domain is described here, and we sketch that domain. This is saying x goes from radical y to 1, x goes from radical y to 1, and then y goes from 0 to 1. So this is saying that x equals radical y and x equal 1 are the bounding curves. Well, x equal radical y is the same as y equals x squared. That's our parabola here. And x equal 1 is our line here. So if we're a point inside this region, we've got on our left x equals radical y, on our right x equals 1. And then with that, y is going from 0 to 1. So this is the region we're looking at. And now we want to describe this region instead of right to left as top to bottom, right? We were given it as a right to left region. Now we want to describe it as a top to bottom region. So top to bottom, we've got y going from y equals 0 to y equals x squared. So y varies from 0 to x squared. And then with that, x varies from 0 to 1. So y goes from 0 to x squared, and then x goes from 0 to 1. And now we can easily integrate this, again because this is a constant with respect to y, so we just multiply by a y and plug in our bounds there. And now we can do another u substitution. Again, don't forget to change your bounds with your u substitution. If you don't do that, then I encourage you to write x equals 0 here and x equals 1 here. But if you just put a 0 and a 1 and you have that integral in u, then it's wrong. So don't do that. But I usually switch them over to bounds on u. And so solving, we're here. And with that, we'll complete our lesson on double integrals over general regions.